In this video, we'll be going over the recursive approach of unique binary search trees. So given an integer n, return the number of structurally unique binary search trees, which has exactly n nodes of unique values from 1 to n. So in our first example, we have an input value of 3, so we have up to 3 nodes to use, and these are the possible binary search trees that we can generate. Inside binary search tree, the left subtree must have values that are smaller than the current root node, and the values on the right subtree must be greater than the value at the root node. Let's go over the thought process. So we are given n possible nodes. Then for each of the nodes at index I, where I is in between 1 to n, we can generate a root node of I. Then we can generate the left subtrees of I using I minus 1 nodes to be on the left side. Then we can generate the right subtrees of I using n minus I nodes for the right side. Then how many binary search tree can we generate with root I? In order to find all combinations, we will need to multiply left times right. So for example, if we have 2 possible left subtrees and 3 possible right subtrees, then if we try to pair them up, it will be 2 times 3, which is equal to 6 possible trees. If we pair up all of the possible subtrees, we get 2 times 3 binary search tree, which is rooted at I. Let's go over the pseudocode. So we're going to implement the recursive approach. And then what parameters do we need? We'll need n is the current number of nodes that we have. And what is the base case? If n is equal to 0 or equal to 1, then we can generate one possible tree, so we can return 1. We can ask ourselves why, if n is equal to 0, we can generate one possible tree. Because if we can see from this example, so if we're currently rooted at 1, the left subtree is equal to null. And then we have 2 possible right subtrees, as we can see here. So these are 1, and then we have 2. So we have 1 possible left subtree and 2 possible right subtrees, so we get 1 times 2 is equal to 2. So we have 2 possible subtrees that's rooted at 1. Then in each of the recursive call, we're going to create a variable, trees, to keep track of the total number of binary search tree, and we iterate through from 1 to n, denoted as I. We're going to recursively find the number of left subtrees. We change n to I minus 1. Then we're going to recursively find the number of right subtrees. Then we can change n to n minus I. Then we're going to increment trees by the total number of combinations, so it's right times left, left times right. Then we can return trees. Let's go over the code. So we're going to validate the input parameter first. If n is equal to 0 or n is equal to 1, then we can return 1. Then we create a variable, trees, to keep track of the total number of binary search trees. Then we iterate through from 1 to n, denoted as I. Then we'll find the number of left and right subtrees. So we'll increment the number of trees by the number of trees on the left side, I minus 1, times by the number of trees on the right side, n minus I. Then we can return trees. this approach is still not efficient enough. We will optimize this in the memorization approach in the next video. Let me know if any questions in the comment section below.